Hi, Josh. We're going to do a video on Euler's totient function or Euler's phi function. This is the second video for the Euler's totient function. Here we will see the application of the totient function in problem solving. Problem number 1 is work out P81, C37, phi, the totient function of 464, totient function of 2560, and totient function of 1000.
Okay, so let this be A, B, C, D, E. So for
Use blue.
A,
You can use blue.
okay.
Okay.
A. P of 81. So 81 is equal to 3/4.
3 to the power 4.
And
What's the formula? Can you write it below?
in red.
Yes.
So P of any prime raised to any integer power is equal to that number minus the power before it. So then 3 to the fourth, we can identify 3 as P and then 4 as Q. So phi of 3 to the power 4 is 3/4. 3 to the fourth
3 to the power 4.
minus 3 cubed. Or 3 to the 4 minus 1.
Yes, and that is 81 minus 27. Yes.
So this is final.
Box it. Yeah, nice box. Yes. That's 54.
P of 37. So luckily, 37 is a prime itself. So the formula for the totient of any prime is simply P minus 1.
Nice.
So easily, this is 37 minus 1 equals 36.
Yes.
Controls up.
Why is it P minus 1? Why is it the minus 1 there? Can you explain to us? That is 37, actually 37 minus 1.
37. Oh, I missed the
Just here,
7.
just please. Just please on the rate.
P minus 1 is actually 37, which is P, minus 37 over 37, or P over P. So eventually, that just works out to 37 minus 1, which is also 36.
So everything actually boils down to the same formula, right?
Yes.
Oh no, you can use still the space below. Try to use it. You might lack space.
See.
You use the total function of 464.
Okay. So
Right,
464 is not neither a perfect power or a prime itself, but it's a composite. So the totient function is multiplicative. And 464 happens to be 16 times 29. So we can just express it as the P16 times P29.
So what formula are you using there?
It's a multiplicative. P of EB equals P of A times P of B.
You can explain to us what is in your problem 464, what is A there and what's B? So just those who are
This
trying
is
to
A,
learn.
this is B, this is AB. You just
Okay.
So now we end up with a similar situation to A and B, but there happens to be both of those similar situations. So phi of 16 is the quotient of a perfect power of prime. So 16 is 2 to the 4. And then the second instance, which is phi of 29, amps. But
29
29
is
is
what?
a prime itself.
Yes. So we're
So
using
we're using both formulas.
the formula for B.
So again, I will highlight. So then this is our P, P1, P2. This is our K. So then that is equal to
You can use
2 to the 4th minus 2 to yes, technology. So oops, times 29 minus 1. And then eventually this is 512 minus
So how did it become?
256. It's just that 2 to the 4th. Oops. 2 to the 4th.
2 to the 4th is
16 itself.
16
Minus 8,
8 and
28. 8 times 28. 24.
yeah.
Back. Yes.
Okay. And the page gets page 2 first.
Basically. So the fee of 2560. Okay. So now this is a much bigger number. So 2560 and its prime factorization. Or I will just divide it first. 512 times 5 equals 2 to the ninth times 5. Okay. So this is, once again, this is a multiplicative function. So we can just multiply.
So 5 there is what?
5 there is our prime.
Yes. 5 is not fine.
Just be, both of these are already prime.
Okay.
Prime.
Times.
So now, 512 is a perfect power of 2 to the ninth times 5. And then we're back to the same situation. Now it is 2 to the ninth minus 2 to the eighth times 5 minus 1.
Okay.
Times 4. It is easier to memorize the powers of 2.
Yes. We tackled that when you were learning the binaries, right?
Binaries, and it's also important in many applications, not just the ones related to computers. Then, uh, actually, I have my own solution.
For the next number?
For the next number?
Yes. Yes. Can you share with us your own solution? So there you go. My own. My
So,
own. Put own.
then,
Those are all your solutions, but that is your own. The ones you solve from A are all your solutions, but this one is your own.
my personal technique. So, n equals it's composed of primes.
Yes, any number has its prime factorization, right?
Let n minus n over its first prime be y. Then, uh, it's sort of the Euclidean algorithm, but in for the totient function,
The first thing is,
you keep doing the same steps to use the, and then you will use
not
the
squared, huh?
step
It's
you
a
got before.
subscript, the two. Be careful. What is zero?
Mm,
No,
it just keeps
Algo
on
number,
going
yes.
until p and q and it is once the pn is also converted sort of. So
Q or phi?
p. Mm, so
Mhm. So how do you apply this?
okay, so
Your formula here.
we
The
once
totient
again
function of 2560 is the prime factorization. Yes.
so once again these are the
To the 9
primes
times 5.
primes
So 2 to the 9 is what prime? Your P number what?
1
Up to there. Bilhin.
P1.
That's your technique.
Okay, so now 2560 minus 2560 over 2. This can get easier if the prime factorization is rather small. It can get really it can get very big. But if the prime factor if it doesn't contain many primes, this will be easier than other methods. This is P1. This equals 1 to 80. And then next step, 1 to 80. It's a reduction minus the next prime is the denominator 5.
Prime number 2 will be the next denominator, yes.
If there was a third prime, then this would keep going. But there are
Yes,
only two primes here.
Prime number 1 and the
So
prime factorization is 2516, yes.
rather magically, I end up with the same solution.
Was
But
that 102? Can you fix your
1024.
digit? It doesn't look like a 4. Make it like look like a 4. Don't try using just one stroke. Yes.
Okay. So
Nice.
we end up with the same. We end up with the same answer
Yes.
for in less steps. But the catch for this, the catch here is that if the numbers are very big or it has many primes in it, it will be rather tedious to do the arithmetic.
Yeah. Okay. What about trying to do your own uh, solution on letter C? Totient function of 464. Can you try that one?
Okay.
If it will work.
C C 2.
Yes, solution number 2, your own solution,
So P of 464. Again, break down into its prime factorization,
which is
which is 16 2 to the fourth times 29. 2 to the fourth times 29. Like 29, 2 to the ninth.
2 to the 9.
No, it's 29.
29, yes. So,
It got too small. It looked like an
this
exponent.
is your
So both of
prime
these
number
now
1,
are
prime number 2.
primes. Anyway, so actually, there's no need for that. So 464. I discovered this by accident, and then I just proved it when I found that it worked. 464. Slowly.
Very nicely. Then next step will be
Next step is to take that 232 and then use the next prime. This only works if the primes are in order from least to greatest. Let's see, is this the correct answer? 224. 224, yes. So it does work.
letter E,
Letter E. So
the
now,
quotient function of 1000.
so letter
E function.
E looks, you can expand letter E into 1 million and it would look scary, but it actually is much easier than the others.
Yeah, it's just
It just looks
that's
big.
a power of 10, right?
So again, break down into its break it down into its prime factorization and use the prime factors. It will be easier if you just break it down. So they are all primes to some power. This is some primes to some power. So 2 cubed minus 2 squared times 5 cubed minus 5
Mr.
squared.
5 nice. Yes.
You draw answer. Uh,
2 cube is
8 minus 4 times 125 minus 25.
yes. Continue below here.
4 times 100 equals 400. Yay! Okay. So,
Nice.
noise. Noise. I don't have the sound effect.
Nice. So can you try your own formula there? The
Algorithm. It's
your
not
own
really a formula unless you
the
can.
algorithm, yes. Your own
It's
algorithm.
not really a
Yes,
formula
yes.
because
Algorithm. I was mistaken.
500 and 5,000. 500. And then 500 over 5 itself. Then that is 400. So now we can see why in the end 2 is eventually a multiple of 100.
Yes.
Okay, so
Let's go to
let's go back.
question
So
number 2.
question
Can you
number 2.
remove the
Moving
singular?
controls.
Yes. Okay.
For how many integers from 1 to 60 inclusive is the fraction n over 60 already in lowest terms?
Yes.
So
Can you explain first what do you mean by, for those who are trying to learn, for our viewers who are trying to learn, what are fractions in lowest terms? Give
in
an
lowest,
example. So
let's say for
okay, let's say
fraction
example 9 over 15. 9 over
9 over
15.
15.
9/15. Let's say 9/15.
This fraction is
What do
not
you
in
do?
lowest terms because
What do you do?
9 and 15 have a common factor. So that common factor is 3. So we can still simplify 9/15ths. Do a much more elegant looking 3/5.
The
So
that
this
is
is in
already
lowest terms because
yes.
I cannot take any number. I cannot take another factor from it and then cancel those factors. So essentially the
So
GC.
let
Okay.
me let me add something first here. For example, excuse me. This is not in lowest terms because of hold on. What's the how do I write?
No,
This one?
no. The previous one was
Which one? Which one?
yes.
So here the GCD of 9 and 15 is 3. So explain to us also in terms of GCD. It means this one, hold on,
It means there's still a
not
divisor.
not yet in lowest terms or simplest. The others they call this as simplest form. Okay, so how about the GCD? What is the GCD of 3 and 5?
It's one.
It's
So
1, meaning
there's a so it means 3 and 5
already
are
in.
already relative to time, or sometimes in British English co-prime.
Okay, you're right here. For our uh, viewers who are trying to learn, 3 and 5 are relatively prime or co-prime. Mean also because with each other. Why? Yeah, there are no more common factors
greater than 1.
greater than 1 between 5 and 3. Yes, so when the GCB of two numbers are is just 1, then they are already in their lowest terms. So let me just add, excuse me, for those who are trying to learn. Like, hold on, can you plug in the so GCB is already 1, meaning they are in lowest terms or in simplest form. Okay,
Yes.
so
So we can use this to our
no other
advantage.
common factors or divisors
So
greater than 1.
essentially, we have successfully converted the problem into mathematics. From lowest terms, now we have a function. We can use the
So
Euler's
we are
torsion
looking,
function.
so here in this problem, because basically we are looking for what?
We are looking for Euler's the torsion function of 60.
So meaning,
The meaning the numbers, let's say the numbers x or number n.
and you're right
Okay.
here, you're looking for what? Because you want them in lowest terms, so we're basically looking for what? The GCD of what? It's right. So it would be easier. Can you type that? No, you're right. No. Just right. The of 60 and 60 and what?
60 and
Oh, what happened? So we are basically looking for what?
we're looking for the numbers
What is
x.
X?
We're looking for the
No,
numbers x.
I don't see any X there.
It's the n for which.
So for the N in when GCD
The
of
GCD of
N
n
and
and 60
60
is
is
equal
equal
to
to
1.
1, meaning because when one and the GCD is 1, it means
It
the
means
function is already in lowest terms. So here, look, oh, wait, excuse me. This is the one I have to press. So here, n over 60, right? Hold on. N over 60, so is equal to, is in lowest terms, meaning this one. The GCD of n and 60 is equal to 1. There are no other common factors more than 1 between n and 60. That's basically what you're looking for. So basically, there, it what's that? What you're looking for? What
we're looking for the totient function of
of?
60 or
Yes, you're looking for the totient function of. Oh, can you fix that one? It looks like 6.
6 of 60.
The phi of 60 or the totient function of 60.
Okay, so now
Oh, you can use another page so we don't, everything doesn't look prompt. So, so this is easy. So, with formula,
multiplicative function.
you can use the
Let's use the
multiplicative
multiplicativity.
function. Yes, multiplicative function of
It's not really the multiplicative functions, the multiplicativity or the multiplicative property of the Euler's totient function.
Write up nicely, please. Write nicely. What's that? What's that number?
Which one?
Is that 5 or what? Don't use
Yes.
one stroke for writing numbers. So applying the formulas you were using before.
The window.
Put down that one. Put it away here. Yes. Just here.
Four
So
minus
they can relate better. Just below. So it's easier to see. Yes. 16. Easy.
Yes.
So, or you can use another uh, formula.
Yes. So that is the alternative alternative way of
Getting
getting the Euler's
TF16.
TF16. So we will need the prime factorization again. So I'll just put it.
Careful. Write properly. Don't rush. Can you write more beautifully?
So this is two, one of the primes. P1, P2,
They become
P3.
the
They become the denominators.
yes.
Okay, so 60 over 15 times 4. 60 times 4.
Oh,
That is
you can factor
240.
that one.
240
You can
times.
factor 60 and 5.
Yeah, wait, 240 over 15 equals 16.
Yes. Can you use your own algorithm here?
Hmm. Okay, so 60, so P1. So 60 minus 60 over P1 is 2. So that equals 30. And then now we will use 30 again. 30 minus 30 over P2, which is 3. So that is 30 minus 10, 20. And then next 20. mhm, 20 minus 20 over 5, which is P3. So 20 minus 4, 16. 16
Yes.
again.
16 again. So let me add something there. What do you mean by 16? 16 is the phi of 60, right? It means this is the meaning. Wait, I will use a different color. It means there are 16 totatives of, excuse me, let me move, I cannot move my hand, of 16. What does 16 totatives of 16 mean? This means that, I cannot move my hand. This, there are 16 numbers from 1 to 60 which are co-prime or relatively prime with 60. I will move this up here. So what are they? So I'll use a different color, pink.
Yes.
So they are 1, 7, 11, 13. 4. Those are 4 already. So I'll put a bar so it's easy. Okay. 2.
This is the 19.
Okay. So 17, 19, 23, 29, 31 is also co-prime with 60, meaning they have no common factors aside from 1. 37, 41, 43, 47, 49, 53, and 59. So wait, I will just divide them so it's easier to count by fours. There. 4, 8, 12, 16. There are 16 co-prime numbers which you can use for as your numerator. And over 60. You can either use any of these 16 totatives here at your numerator, and the fraction that you will get will be in lowest terms. So can you put me to another page, please? I will just finish explaining this one. Meaning, so I can use n over 60 is in lowest terms when GCD of n and 60 is equal to, when GCD of n and
1.
is equal to 1, meaning there are no other common factors between n and 60. So I can plug in any of those 16 totatives. Let's say examples will be 1 over 60, 7 over 60, any of those 16 totatives that we got. Oh, can you bring me to the previous one? There. 1, 7, 11. I can plug in any of uh, these 16 totatives as my numerator, and I will get a fraction in lower terms. So 11 over 60, 13 over 60, that up to 59 over 60. So that is the meaning of the totatives. So that's all, folks.
That's all for the day. Yes.
Say hi. Say,
Hi. All right. Bye.
bye.